cool. Yeah.
Hi, welcome to Chemistry 139, the second edition of the double session. Are you guys getting all this? I hope. Good. Here we go. We've been talking about odd electron species, okay? Octet exceptions, up there, okay? And we looked at something like nitric oxide, right, which is an odd electron species, only 11 electrons, 11 valence electrons. And that exists, and again, you probably have smelt it coming out of a car exhaust. It actually has almost like a bleach smell to it. It's not the sulfury smell, but more of a bleachy, sharper smell, and that's nitric oxide. Okay, so that exists and is fairly reactive, but again, you do have radical scavenging or odd electron scavenging species. So let's think about some other exceptions. Here's one. BF3, best friends forever, forever, right? How many valence electrons? 3 from boron, as we look at boron's column 13, but that's 3 electrons to us for the valence. And then 7 times 3 for the fluorines, so that's 24 valence electrons. Okay, so 24 valence electrons, great. You can work with that. Let's put boron in the middle. Okay. Least electronegative element. More electronegative elements out on the ends. We'll go ahead and give the fluorines what they need for the octet. And lo and behold, we've got 24 valence electrons. And we're done. Boron does not need the octet. We don't need to double bond a fluorine to give it the octet. That would actually give fluorine a pretty high formal charge. So
you missed 2 electrons.
And I missed 2 there. Thank you very much. So there we go. We do now have actually 24 valence electrons showing, but boron is said to be electron deficient. Okay, so this is an example of an electron deficient atom. I think I spelled that right. And that's fine. Boron does this. It's okay with 6 valence electrons around it, not 8. That's kind of how it plays the game. All right, so that's an exception in that regard. Totally fine. And then, we see odd electron species, electron deficient species. We also have what are called expanded octets. So I'll go ahead and erase this just to be in line with the camera here. And we'll look at sulfur hexafluoride. Okay. Going with tradition, we've got 6 valence electrons from each sulfur. And we've got 7 times 6 for the fluorines, and that's going to give us a total of 48 electrons.
What was this one called?
This one's, expanded octet. Thank you. All of these, again, exceptions to the octet rule. So if we go with our method, least electronegative atom in the middle, more electronegative atoms outside, we do end up with a structure. I'll give it some perspective here. All right, kind of like the darker lines are coming out at you, the dashed lines going behind, and then these 2 fluorines are in the plane of the board. Okay. Pop in our lone electrons. And there we go. We have 8, 8, 8, 8, 8, 8, and 8, 48 electrons all showing. Right? But look at that sulfur. How many valence electrons does it think it has? 12. Right? So what have we done? We've expanded the octet of sulfur, which now has 12 valence electrons. It happens. Okay. These things are totally possible. We've also seen that phosphorus can expand its octet. So in something like PCl5, we get this structure. That should be about 35. I'm going to double check. We got 5 from there. 7 times 5. Actually 40 electrons, I should say. So that's a 40 electron species. And we can get those 40 electrons around that molecule just nicely, but what happens? We expand the octet of phosphorus. It has 10 valence electrons around it. That's another expanded octet. So, exceptions. What can you count on? Pretty much, as we look at the periodic table, carbon, nitrogen, oxygen, and fluorine follow the octet pretty religiously. You can count on them to always have 8 in any configuration. And of course, hydrogen always 2. All right, so those are the few atoms that you can really count on. Everything else can have some exceptions, right? But in general, we do follow the octet rule pretty well.
Is that where we get into like iron, nickel, and copper, and those ones in the middle there that are weird?
When you get into the transition metals, the D block metals, you're going to see more types of bonding that are possible, more bonds.
More about the structure.
Yeah.
Okay.
Because you also have more valence electrons in different orbitals, and that can lead to some changes as well.
So basically, their valence electrons, like it increases by 1.2.
Yep. And weirder stuff can happen too. I mean, some people have done. I think I can draw it over here. Yeah. Take SF6. Well, what if you did this? You break it up into an ionic compound, because SF4, 2 plus, okay, if you think about that, that's got that's 32 electrons, right? And then the 2 fluorides are 8 apiece themselves to give you 48. But wait a minute, it's ionic. That's weird. Well, it just so goes that sulfur hexafluoride, nonmetals, which should be covalent, actually there's some ionic character to the bonds. So this is kind of an extreme form of that. This is kind of another extreme form. This is like the pure covalent, that's the pure ionic. But it's actually somewhere in between. Right? So we don't get into those kinds of discriminations, right? But that's what we're seeing here, that the model, the Lewis model, is not really going to tell us the whole story for these. We need something better. Eric?
Why is it 32 and not 30 for electrons?
For this one?
Yeah, I thought we would lose 2 because it's plus 2.
Well, what I've done is also to the 2 plus is probably coming from a formal charge on sulfur being plus 2. So it's kind of like sulfur's given up electrons to the 2 fluorines outside. That's one way to think of it. But that's not even correct. Right? I mean, again, extreme, it's something probably very different. Okay? But it gives you a sense, right, that there is a kind of a really interesting aspect here to bonding, determining where those electrons are going to be. So, we've got these octet exceptions, right? Expanded octet, we've got electron deficient with boron, and we've got odd electron species. Okay, so they exist. Do I focus on those? No, we're going to focus on the octet rule and the duet rule. That's going to be our goal. Okay. Looking ahead, let's think about maybe since we've been looking at covalent compounds, maybe a brief look at metallic bonding, just to kind of round out our discussion of bonding. So we've looked at ionic, metal and nonmetal, transfer of electrons, you make charges that attract. Covalent, right, we see that we can share electrons to get to stable molecules that satisfy the octet as well. What about metals? Metallic bonding. Let's think about that a little bit. So what I like to do is, first bring up Star Trek, right? Dilithium. Any Star Trek fans out there? No? Okay. Showing my age here. That's all right. Dilithium. Does it exist? Maybe only on Star Trek. But let's say we wanted to make dilithium as an ionic compound and as a covalent compound. How would we proceed? Well, let's get the Lewis dots. Right. Lithium, column 1, 1 valence electron. If we want to propose an ionic structure, one lithium could donate an electron to the other, and we get charges. So we do something like this. Right? Just transfer to charge. Kind of just playing this out. All right. Li plus. What is it isoelectronic with? What other element? What is it? Helium. And what's lithium minus isoelectronic with? Beryllium. Well, hey, lithium plus, we're kind of liking it, right? Achieved a noble gas configuration, but beryllium's not a noble gas, right? It's got a filled 2s orbital, but it's not a completely filled shell. So to us, right, while the charges look nice, we can have attraction, the electron configurations are not what are to be expected. So trying to make ionic dilithium doesn't quite make sense. Well, what about covalent? That might seem more reasonable. Let's just take those dots or electrons and we'll share them. Okay? We'll just go ahead and make a shared pair. Well, what's the lithium think it is now in terms of the element? Beryllium, and of course, beryllium. Not a noble gas configuration. Not likely stable. Can you make Li2? It's possible to make it, in a very low vacuum laboratory condition, and provide energy to keep it just as a diatomic molecule like this. But otherwise, typically, how do we find lithium and other metals? They are clumps of atoms bonded together in another type of bonding, metallic bonding. So let's take a look at that. So instead of getting molecules, right, you actually get many atoms bonded together. Just pretend this is a solid. This is solid lithium. But what's going on to make the bond in this case? How are we getting attraction? Well, how many valence electrons does lithium have?
One.
Just one. So here's the thought. Here's one idea. That those valence electrons, they're there, but they're very loosely associated with the atoms. And so this model is typically called the sea of electron model. Okay? And in fact, these electrons act almost like a gas above the nuclei. just the valence electron, that's all you need, just those one electron, are moving freely above these nuclei in the bulk solid. So if you think about that, right, why might that help explain what metals do? And you tell me, what are metals good for?
Conducting electricity.
Conducting electricity. So you think about putting a voltage across your metal. So typically the shorter line is the negative terminal, the longer line is positive, okay? So effectively, what is a voltage? Really, it's a source that brings in electrons, okay? So we're going to bring in electrons to this side. And what happens when an electron meets up with an electron here? It's going to repel. What that electron will do is move over toward that electron. What will happen? Repel, and repel, and repel, and repel. And you just basically get that, old story, right? And the little one said, roll over. So they all, you got that, right? So we don't have electrons literally going from here over to here near the speed of light. Why is transfer of electrons, circuits, why is it so fast? It's because it's an influencing effect that moves very quickly throughout the whole crystal, right? So that repels, that repels, that repels, that repels, that repels, and that moves your electrons in that way.
They keep
They
going
keep
back.
going around, okay? So that can only happen if your electrons are delocalized. So that's the term that's used. They're highly delocalized. They're not localized on the atom. They're delocalized among all the atoms. Right? So sea of electrons. Those are delocalized electrons. Right? So conductivity is explained by that model. You can also begin to see, too, why metals tend to be also malleable. What's malleable mean again?
Being smashed.
Smashable, right? So if we were to smash this line of atoms down, the bulk of the atom moves down, right? But since the electron's not really associated with it, it can quickly readjust so that you don't have any repulsion between the nuclei, right? You can easily move that, smash it, it adjusts, and it's back to being the metal again, right? It doesn't lose that bonding.
Since all the electrons are like fluid,
Yeah.
wouldn't like taking one out, you could like easily take all of them out, just as easy. Just
It's the idea.
Like liquid in like a cup, like you move.
In essence, could you kind of pour out your electrons? Now, here's the thing. Another way to look at this is, let's see where my. Can I draw over here? Yeah. Okay. Good. I'll have to talk to my audience then. So another way to think of this is, and this is just looking at a set of lithium cations. The nuclei are down here. They're like at the bottom of a well in each case. And what are those sea of electrons doing, right? They're kind of moving freely above, right? They're not solely associated with the atom anymore. They're moving like a gas or liquid above. And people actually think more like a gas. But what do they do as they get near the nuclei? They kind of feel the love. They get away, they feel the love, they feel the love, they feel the love, right? So they're always going to be slightly attracted. So in that sense, you can't just pour them out or dump them out as easily, because there is still a force of attraction between the sea of electrons and the nuclei, right? So another term for metallic bonding, this is all talking metallic bonding. Right? It's not ionic. It's not covalent. I think I'll borrow Stephen Zumdahl's description of it. It's delocalized covalent. There's sharing going on, right? But it's because of this delocalized electrons that we get the properties. So we call it delocalized covalent. It's a good term because you already know what covalent is, and this gets that idea of the sea of electrons involved. Yep.
So is there no Lewis dot structure for
You got it.
the delocalized?
Yeah. You can't do Lewis dot structures for metals.
Is there
There's a theory.
Structure?
There's a theory that,
Okay.
and it's called molecular orbital theory that you can. We learned a little bit about it in Chem 163, so you do get to an explanation of that a little bit more. Yeah. Yeah. So that's kind of cool. Yeah. Go
Molecular
ahead.
what was it?
Molecular orbital theory. MO theory is how it's often called.
So if we see two metals on a test and you're trying to get us to write the Lewis dot structure, we say no.
You
It's
say
still
no.
Lewis equivalent.
I need more information. Right? Very good, good. So, just another aspect of bonding. We don't focus much more than this on metallic bonding until later on in your series, right? But it gives you a good way to round out the periodic table because we've been focusing on kind of positioning ionic compounds, kind of far left metal, far right non-metal. Covalent compounds, pretty much right-sided to the right of the staircase and on the staircase elements. But we know most of that periodic table is made of metals. So we should talk about what's going on with those. Okay, but it is a kind of cool type of bonding that leads to the properties that we see metals having, like conductivity and malleability in that regard. Okay. Other questions on that? Pretty good? And again, we've looked at exceptions, and what we want to get back to really is the basics and think about polarity of bonds. That's kind of the next thing to look at. So we can bring some of the molecules we just did on the board and start to think about polarity of bonds. That's also some of your homework where you're dealing with electronegativity tables and so forth. So you can bring up a homework question if you'd like, but I'll just use some of the molecules that we've looked at already. So, given that, I think the one I am thinking of right off the bat is the PBr3 phosphorus tribromide. A binary compound made up of just phosphorus and bromine, but we need to use the tri to specify the number of bromines there. Okay, so we had, I think, 26 valence electrons for that. And we had a Lewis structure like that. Okay, all 26 shown. Okay. And the first thing we want to look at, once we've got that Lewis structure, that's your first task. Get that done. Now we can start to assess the polarity of the bond. All right, and so we'll go, in this case, the bond is all the same. It's a phosphorus-bromine bond, but we want to assess how polar that is. And then I'll underline the bond because this is kind of how I want us to proceed with a method, right? We're doing the Lewis dot method just to get the organization of the electrons and the bonds. And then we want to look at the polarity of the bonds. Later on, we're going to add the polarity of the molecule, right? Very specific in that terminology. So this is our focus here, is what's the polarity of that bond. And what do we use to assess that? What do we need? Pauline's. Yeah, what are those called, those values? Electronegativity values. Yep. We need the electronegativities of those. Now, looking at the periodic table, we've got essentially, for you at home, you can look at your periodic table, but we've got this relationship between phosphorus and bromine, okay? So, what do you think? Who's more electronegative?
Phosphorus.
Phosphorus you're going to go with? You're saying bromine? So let's think about our trends as we go left to right. What happens to electronegativity? It increases. As we go top to bottom, decreases. Do we have a way to...
CL, yeah.
What's that?
Chlorine.
Chlorine, but we're working with bromine.
Bromine is 2.96.
That is,
We'll get to that in a moment.
They're probably equal.
Well, let's think about how many steps do we have to go over to chlorine? 2? But we only went 1 down.
Yeah, but we still went over 2.
So I'm thinking that the effect going across might be stronger than going down.
Yeah, because when you go from, what was it, hydrogen to lithium, it dropped like a lot every time you go down.
Okay,
Is that
going
usually-
going down, it seems to drop a lot. So you've got values though.
Yeah.
What do you got?
Bromine is 2.96 and phosphorus is 2.19.
And what did I say? Was I making a comment as to which one was more electronegative? Did I say anything? I don't think I did.
I don't know.
So, do we agree with this? We're over 2, but only down 1. So I would think bromine would be more electronegative than phosphorus. That makes good sense, right? We're not going 2 down, where I think, Trevor, you're thinking they might be equal. So, possibly, or 2 up or something like that. So I think, yeah, we've gone over 2, only down 1. Bromine is essentially more to the right of phosphorus in that regard. And that's kind of what we're seeing here. Now, am I going to have you guys memorize these values? No. You're either given them or you can use trends, kind of like what we did here a little bit. But this is, something that I would give you if I want you to work with the numbers. All right? So, we've got to calculate delta En, the change in electronegativity. Okay, so that's going to be just the difference. It's always a positive value, right, in this regard. So that's going to be 0.77. Okay, and then on our scale, polar. Okay, so yeah, definitely greater than 0.5. Okay, so we're going to say, hey, that's a polar bond.
I was noticing doing the homework, most of them are polar. They're not ionic, they're mostly polar.
Right. If you're working with non-metals, right, and just comparing them, you're usually going to get polar bonds, unless they're really close together. Maybe like silicon and phosphorus might be more non-polar, where silicon and chlorine are definitely polar. Okay, but here we go, right? That bond's polar. That's the same kind of bond. That's polar. That's going to be the same polar, right? So what we can do is draw those dipole moment arrows on our Lewis structure. Okay? And so that's kind of the way I'll proceed with the questioning is here's a formula. Count the valence electrons, get the Lewis dot structure. And then I'll ask you, are the bonds polar or not? And you should be able to demonstrate a calculation or use the trend. And then show that polarity using dipole moment arrows.
So you can have more than one dipole moment.
Yes, and so let's look at something a little bit, where there's some difference to it. So if we were,
But with
go ahead.
water, it was showing just the one because of the way it was shaped. Is that just a interesting...
We'll get to that. We'll bring in shape in a moment. We'll just kind of look at molecules.
Okay.
And so I'll kind of move things along a little more quickly here, but if I did something like, that molecule, okay? Let's run with our what we know first, and then we can put in the numbers. Nitrogen and hydrogen, where are they relative to each other? Hydrogen's to the left of nitrogen. All right, so where's our dipole moment going to point? Toward nitrogen.
Towards the nitrogen.
So that's going to be the true there. And then nitrogen and bromine. There's a tough one. We go 2 over to fluorine and 2 down to bromine. Don't they kind of counter each other? Might they be the same electronegativity?
But we know that going down, you get the difference is greater.
Okay, so you're going to say nitrogen's still probably more electronegative? So the prediction is it's going to go that way. So let's get the values.
Values. Hydrogen is 2.2. Nitrogen is 3.04. And bromine is 2.96.
Hey, we did well, right? Definitely that's going to be a dipole in that direction, dipole in that direction, dipole in that direction. Okay, let's get some, I mean, that's going to be fairly polar, about 0.8 something, right? And this one, not so polar, right? I mean, is it? Yeah, it's really quite low, so we could probably even get rid of that arrow there.
Let's say that one was just covalent.
Just covalent non-polar, right? Because difference there, right? Just for completeness sake, right? We're looking at 0.08, effectively non-polar. Okay, so no arrow needed for a non-polar bond. So then we've got these 2 remaining dipoles. Okay, so are the bonds polar? Well, yes, some of them are. Okay, and what's that going to do? That's going to lead us into thinking about now the polarity of the molecule. We've got parts to that question, right? To answering that question. Right now, we're just looking at the bonds and asking, are they polar or not?
So the arrow pointing towards like nitrogen, so the nitrogen has a greater pull on the electrons than hydrogen does?
Yeah. Yep. And that's what we're doing, just based off of the electronegativity. Just because, nitrogen's got a little bit more of that proton pulling power to draw electrons to it. Okay. Other questions?
Normally we want to see more electronegativity like going outward, so there's more space, but hydrogen's the exception, which is why it's always terminal and
Right.
pointing. So we'll see that always with hydrogen.
Always with hydrogen.
Pointing in.
Yep.
Okay.
And that kind of, that does lead to some interesting aspects, particularly with something like water. Okay. So in that regard, right, we're where we need to be. We've got Lewis structures. We understand bond polarity, which results on kind of the pull on the electrons due to the nucleus and differences in the nuclei. But what we want to also get to is understanding what these things really begin to look like in 3 dimensions in space, right? Because we're still dealing with matter that is 3-dimensional. Even though it's really small, we can't see it. We know when we pack up a lot of water molecules, it takes on the shape of its container and so on and so forth. So we've got to come at understanding now a little bit more of the 3 dimensions from 2 dimensions. Okay, and that's really going to bring up, our next topic is involving big long statement that we're going to abbreviate. To VESPR, right? But it is called the valence shell electron pair repulsion model for 3-dimensional structure. Okay, but you can already begin to see what's happening here, right? We're back to this idea of electron repulsion is key to understanding what's going on in these molecules. I mean, there's attraction as well, but we've seen repulsion has a bigger role because if we bring electrons too close to each other, they're going to repel, and that's going to be high energy. Right? So this model really is going to go back to thinking about how to get electrons as far apart as possible. But we're going to have to think about the types. Okay. So just to kind of do a little preview, we'll go back to a simple molecule like CO2 in that regard to bring that up. So right now, right, if we just put up CO2, there's the formula. That's one aspect of structure, right? What are the atoms that make up the compound? Carbon and 2 oxygen. That's telling you structure. It's not three-dimensional, but it's telling you something. We've got 4 valence electrons, 6 each from the oxygens, total of 16 valence electrons. So, with a little bit of help from multiple bonding, I can get all my 16 electrons arranged in a nice symmetric molecule. Okay? But right now, we could ask the question, thinking about geometry, is the molecule shaped more like kind of a barrel, or does it have a kink in it with a 90-degree angle between bonds? Right now, these are both correct structures, right, because they follow what we've studied. Lewis dot structures. Do we have all valence electrons accounted for? Yes. Do we have everybody having the octet or duet if it's hydrogen? Yes. Done. Fine. But we may be well aware that CO2 is actually this more barrel-like or straight or linear structure. Okay? And if you begin to think about this molecule, the bent one, right, what are we doing? We're taking and bending those bonds toward each other. So you're now bringing lone pair electrons closer to lone pair electrons. You're bringing bond pair electrons closer to bond pair electrons. And to do that, you have to add what? Energy. Because what are those electron-electron pairs doing? They're trying to push away. Right? So you're going to have to overcome that push away by adding energy. Right? And that's going to be just a very high energy form of CO2. It's not that it can't exist. It's just that to maintain it, you're going to have to maintain energy on it. Right? And so if you don't, if you let go, that's the favored structure. Right? And we literally do see CO2 is a molecule that has a bond angle of 180 degrees. And we do, in fact, call this a linear structure. Okay.
And this doesn't require any energy, or just a very small amount of energy?
Well, it's really, in comparison to this, no energy, right? Because you've got the maximum angle separating all electron pairs. Right? So it's going to be just like that anytime we do know CO2 does do this. It absorbs infrared light and bonds can vibrate and it can bend a little bit, but it's not going to be able to hold that position without maintaining lots of energy on it. It'll come back to some kind of equilibrium wobble. Okay. But we're going to need to find out how to get to this in other structures from the Lewis structure. And what that's going to involve is determining the number of electron clouds around our central atom. All right. So right now, what do we see? We see 1, 2, 3, 4 bonds. We're not counting bonds. We're just going to count how many regions of electron density we see around that central atom. So for this one, right, we're going to say that carbon has 2 electron clouds around that central atom. We're looking at central atoms, counting the clouds. And so I'll just kind of end with this, right? A double bond, one double bond is considered a cloud. A single bond is considered a cloud, a triple bond is considered a cloud, and a lone pair is considered a cloud. They're all regions of electron density. And so that's what we're going to be doing. We're going to be building structures, counting clouds, predicting geometry, layering in our bond polarity. We can do that. It's getting kind of messy here, but if I put my dipole moments there, because oxygen's more electronegative than carbon, right? So what's going to happen in a tug of war when two people are pulling on the same rope with equal force, and you've got a handkerchief tied in between? Is that handkerchief going to move? If they're pulling equally, it's not going to move. So what do we think about here? We have dipole moments that are moving, apparently charge due to electronegativity, but they cancel each other out. And there's ultimately no net charge on the molecule. And so that leads us to seeing that CO2 is a non-polar molecule. Non-polar molecule now, which contains polar bonds. Right? And that's where we can start to get a little bit confused. But if we go through a process, right? Formula to Lewis dot structure, to geometry, to bond polarity, and then to molecular polarity, we're going to do okay. But if we kind of try and start one process before the other, it gets confusing.
So if they're equal on both sides, then it's going to be a non-polar molecule with polar bonds.
Yep.
Okay.
There you go. We'll look at more examples, right? We're going to have to talk about water and ammonia. You can even look at boron trifluoride again. That's a useful one to look at bond polarity and molecular polarity. So it's just another method, right, that we're able to use. Simple but effective, and it gets us now to a little bit of three-dimensional structure, which is kind of cool. And that, I mean, again, once you've got Vesper down, right, that's something you can use, say, in an organic chemistry class all the time. It's really a powerful, simple method. Thank you for staying. Thank you for watching. Thank you for our note takers. We'll get this up on the website for everybody to follow through. Thanks, Trevor.